should be able to do. I probably wouldn't just use one leg.
I think that's sufficient.
Will it locate people? How many people? Can they crawl and still be detected?
It's on a straight part.
Hi, I'm Scott Moore, and for our project requirements, the completed design will do several things of interest to the consumer. First, it will track all the people in the CEL Smart House room within a 10 by 10 foot area of interest. Even though the room will be limited to a 10 foot by 10 foot room for this project, it will be scalable by adding a larger sensor network. The concepts will work for any size room. Specifically, the system will determine the total number of people and also be able to track their locations. The locations will be accurate to a resolution of a square foot area. Since a typical room contains obstacles such as furniture and other human beings, the design must also be intelligent enough to accurately identify a person even when they are partially obstructed. The system will also assume the density of room occupants never exceeds 1 person per 9 square feet. The system will be able to accurately recognize people walking as long as they have at least their head above the obstacles in the room. Otherwise, it will just know that they are present. It will identify a person in the back half of the smart room in the cell. It will also identify a person by any part of their body and will place them accordingly. After processing all this data, the system will output the results in a friendly visual manner to the consumer. The system will pass information to a web server through an Ethernet port, and a grid will be displayed to the user to show the location of everyone in the room, including the super user. Within the room itself, there will be a designated area that is non-accessible to normal people, but is accessible to a super user. The super user has to wear a unique article of clothing so that the system will be able to identify the person. In doing so, it will be able to recognize some type of pattern or code that the super user naturally exhibits. The system will be able to recognize when a super user is entering the restricted area and when a normal user is entering the restricted area. Okay, for my part of the contribution to the project, you can see the servo running. Mounted on top of it is the ultrasonic rangefinder, and it is taking readings at every increment as it turns around. The servo is being controlled by this servo controller here, which accepts a serial input from a UART command from the custom PCB board that I designed. It sends the serial UART command to the servo controller, and the servo controller converts it into a pulse width modulated signal, which controls the angle at which the servo is resting. The rangefinder is taking readings and sending them an analog response to the A to D converter on the custom PCB board, which has built into it a filter, which is doing low-pass filtering to get rid of the noise. This information is then being taken into the PIC processor here, and then being distributed across I2C to the Spartan board.
Okay, I'm David. My responsibility for this project was to detect a super user and distinguish him, determine his location so that the hypothesis thread can distinguish him from the other users. The way I'm doing that is by forcing the super user to carry a cluster of infrared LEDs. The red one here is just an indicator light. These are infrared that operate at a wavelength of 850 nanometers. And the super user will be carrying this around. Ideally, it would be on his head. And we have a camera, this guy right here. This is a low-resolution camera that operates over an RS-232 interface. And I have placed a long-pass infrared filter over the lens. This will, of course, this will cause very little light of the visible spectrum to get through the lens, and these guys will show up like a bright dot on the resulting image. So that thing's hooked up over RS-232 to a converter circuit, which converts it to 0 to 5 volt levels that my PIC can read. And so my PIC pulls in the data real time. Can pull in about 1 frame every 700 milliseconds, and it's about 8-bit grayscale, 80 by 60. Analyzes the image, tries to find the location of this little cluster of LEDs, sends them across I2C to the Spartan board. So we're going to do a little demo. What I have right here is a grid showing all the different locations of the image as I take my infrared LED cluster and move them into this playing field. Comes up with these dots have numbers on them. 1 indicates the most likely position of the LEDs, and these are less likely positions. So as I move across the field of view, as you can see shown up in the image, it's moving across. So this grid corresponds roughly to the grid that Scott's ultrasonic panning sensor will cover. So that's about it. We are now going to demonstrate our system functioning.
So here we have, again, this is the servo, is surveying the room, and up and running also is the camera taking the infrared film footage and analyzing it. Both of these items are now communicating across I2C to the Spartan board, which is analyzing it and sending it to our web server. We are going to clear the room for a second and allow it to get a good baseline. So we're going to step back and let it, it's going to now rotate through our entire 18 angles. Okay, so now that it has the baseline, we're going to step into the grid, one user. So now, as you can see, it registers that there is a user in spot in the same position that I am on the grid. Now if we move over here and bring in 2 users, you can see that it will now pull 2 users up onto the web server. And if we add now, if one of the users becomes a super user, by turning on the infrared LEDs, it registers on the screen, communicating it over I2C from the PIC. And you can see now that the second user has become a super user. If we take it, scoot over, yeah. The super user is now moved, switched users, and moved slightly to the left. This concludes our demonstration of our working system.
I did the I2C communication on the web server, and the way it works is there's a timer on the Spartan that runs at 20 Hertz, and every time it receives a message interrupt, it sends a message to the I2C bus. And the I2C bus, depending on the message type that the timer sends, either forwards a message to the ultrasonic or forwards a message to the camera. And it pulls the PICs, waits for the PIC response, which sends back to the I2C bus, which forwards it to the hypothesis thread.
I wrote the hypothesis thread, which basically relies on data from the timer thread, as well as data from the I2C coming from the camera and ultrasonic sensors. I used the data from the ultrasonic sensor and the camera to establish a grid of probabilities that looks something like this. When I get data from the ultrasonic, I map it using trigonometry to just figure out where in the grid a user supposedly is according to the ultrasonic. Because the ultrasonic is not necessarily reliable, I come up with probabilities based on where it is. For instance, here, the ultrasonic told me it was here, so I've said that there's a high chance that it's here. However, there's an equal, or not an equal chance, but a slightly lesser chance of it being in the bordering cells. I use the timer thread to time when I should send messages to the web server. I also use it to determine how often I should reduce the probability based on time. I'll use the decay function to reduce the probability so that if a user has moved, there's no longer a high probability of a person being here. After a certain amount of time, I take the probability grid and map people to the grid and say this is the highest probability from this section, so therefore there is likely a person there. I then take that information and pass that to the web server. Our sensors typically provided adequate data, however some problems were encountered. The servo-mounted ultrasonic sensor data rate is too slow to properly capture movement. The rate can't be increased because of the setup time required by the sensor. We were unable to use the infrared sensor because of timing required by the analog to digital converter on the PIC collecting the data. This A to D is already responsible for the ultrasonic data limiting its usability for reading the infrared sensors. The camera which predicts the super user's location has trouble seeing the unidirectional infrared LEDs. The environment also introduced some limitations into our project. The ultrasonic sensor needs a smooth backdrop to create the most accurate data. Due to rough backdrops, the ultrasonic sensor can read considerably different distances for the same point. The ultrasonic sensor requires that furniture either be part of the baseline, not moving, or below the line of sight. The camera requires proper lighting to eliminate infrared noise typically caused by incandescent light bulbs. However, typical fluorescent lights do not cause problems. Reliability also became a factor in our design. Our main problem with reliability was the web server's inability to run for long periods of time. We are not sure what caused this issue. Also, sometimes our I2C communication fails after a fairly long amount of time.
I'm here to talk about the improvements that could have been made to the design. In terms of the final design being the overall requirements, the project generally achieved success. However, there were a couple of concepts that were never fully implemented. The first was the idea of setting restricted areas in the room that only super users were allowed to stand in and verifying the person's status. Ideally, we also wanted our design to be able to have a high level of accuracy by keeping track of the total number of people in the room and intelligently figuring out if the person in a new but nearby location was in fact another person, or rather the same person who had walked a couple of feet. Finally, we had previously mentioned that the system would be able to detect a person based on any part of their body. The final design requires the person to be at least the height of the ultrasonic sensor. The project's level of reliability and robustness for the most part is fine. As previously mentioned, the stability of the web server and I2C communication means the system will fail from time to time, but there are also ways to improve the design. If we added more sensors, we would be able to get a more accurate reading of the area, as the different points of data would allow the hypothesis algorithm to cross-check the information with one another. The most expensive part of the component of the system is the RS-232 based camera. We could have used a less expensive camera at the cost of a complicated parallel interface.